Okay, so this is work solution 12. So it's another example where we've been given the neutral axis. So I know the distance from the neutral axis to the lower base and also the upper part. So I'll be interested in analysing the stress that's occurring at these parts of my girder. If there's a negative bending moment, that causes compression at the bottom. So for negative bending moment, it's going to be hogging. Okay. And so we're going to have compression on the bottom, and we'll have tension on the top. So if we have a 15 kilonewton 15 kilonewton meters negative bending moment, I can use my flexorial formula to find out what the tension is going to be at the top and what the compression is will be at the bottom. So this is given to me from my bending moment diagram, or in this particular case we're told it from the question. The distance we're going to measure from the neutral axis to the top section, and this value we've previously worked out what the second moment of area is. So that tells me what the tension is. So we've got 66.6 megapascals. Looking at the bottom, so notice where y is pointing away here, so because we're sagging, so y always goes away from, forms I suppose a little kind of bow and arrow type shape, doesn't it? So you could, if you wanted to, put a minus here in terms of this distance. You don't have to, because we've emphasized the fact that it's in compression there. Okay, so what's going to change here? The bending moment won't change, we're at the same location. Second moment of area doesn't change. What changes is the distance. So this is our distance here. Again, I could have put minus 72 because I'm looking at y going upwards. So I get a compressive force that's larger than the tensile force, and the reason for this is simply because y is bigger. So the bigger the y, the more tension we're going to get. So we've got a small y to get to the top, a big y to get to the bottom, away from the neutral axis. Now imagine a positive bending moment. So if you can, that's your shear graph. We've got a single load, and we end up with a positive bending moment. So we've got a positive m value. So this is a case where you have sagging going on. Your y should be pointing straight downwards. That's my two pivots there, and the load is pointing downwards, and I've got the y going downwards this time. So we've got a positive bending moment. In this case, this is going to be in tension. So the lower bit of the beam, as we look at it side onwards, we've got this being pulled out, and this getting squashed in at the top. Okay, now we've got 8 kilonewton meters being applied. So using the flexorial equation here, the m we're going to put into here. The y to the top will be the compressive y. The I won't change from the previous example, so we're going to have the same value of I. Notice that this is in millimeters. If you've got values like -9, -10, that sort of thing, up to -12, then you'll know that you're dealing in meters to the power 4, which means I then need to convert the 30 millimeters into meters as well. So divide that by 3000, or you can just tag on a 10 to the -3 to your number. Here we got the final result, so that's megapascals. And then for the bottom, this time these are going to be in tension. Just going to wham in the values there. Got the M. The distance to the bottom is 72. The I previously found. So put in my values, and then I can see I've got more tension on the bottom than I have in compression at the top. Now let's imagine that we've got a direct load applied at the centroid. So that means that because I'm applying the load at the centroid, I'm not going to create any bending effect. It's as if I'm going straight down a line that isn't causing it to bend. So we are in effect got a very small deflection anyhow. And I'm going to apply a load so it either causes tension or compression. So I could either be pulling it out to cause tension, or squashing it to cause compression. If we're squashing it, let's say you're working with a concrete reinforced beam, they tend to be in compression. So you've got wires in there which you release, and then they want to compress the beam. So if we've got a compressive load, then what's that going to do to our numbers? The first thing to do is to work out, based upon the force divided by the cross-sectional area, what direct stress this is causing. So we'll just use simply force divided by area. So to work that out, I'll work out the area of these two sections, multiply them by 2, and then work out the area of this top section. So there we go. I'll work in millimeters and then multiply my final answer by 10 to the -6, so I'm working in Newton meters squared. The force, watch out, it's got 100 kilonewtons, so we'll change the kilo into 10 to the 3. So this is going to be my direct stress that we're applying. I make a note that this is going to have this is supposed to have a compressive stress effect. So if we come back to our previous results, so the first result was that I got a bend in tension, which would be at the top, and then I've got a compressive tension at the bottom. This is for a negative bending load, so we're hogging here. So what are we going to do to our numbers? Well, what we could have done is we could have said the last force is a compressive value and called it a minus, and called this also minus, add numbers on. Okay, but because I've neglected in this particular presentation to put the negative value there, I have to take into account of whether it's compressive or in tension. The other case I considered was where we had the sagging case, so from 8 kilonewtons of positive bending moment, and we had these two values. So if it's compressive stress, it's going to make the compressive stress bigger, And in terms of the tensile stress, it's going to cancel one another out, potentially anyway. So for the first of all, we'll work out what the direct stress is there. That was the, what's the previous value? Okay, so that was the force. So this is our stress, and we know it's compressive. So the maximum tensile and compressive stresses can now be found adding the value caused by bending to the direct stress. So for, well, we're starting at the bottom. So for this one here, it's in tension. This is having a compressive stress effect, so we've got a positive tension, take away the compressive stress. So overall the tension in the beam is going to be reduced. Whereas for this case, so we've got a compressive stress. What I'm going to do here is I'm going to convert that back into a minus number before I do any further calculations, and then add on another minus number, and then overall we're going to get a larger negative compressive stress. So here they're recommending, when you get to this stage where you're going to combine stresses together, convert these so that they've got minus signs, and then convert these, and then you can just add the numbers together.